Okay, this is a challenging UT Quest problem. Our forces in accelerated motion. You're basically given a block on an incline. The problem kind of gives you a graph of vertical and horizontal distances. And from there, we have to do a little bit of trigonometry, find the angle of the incline. And we actually kind of begin here with just some trigonometry to really figure out what theta is. Okay, they tell you that this block is some sort of horizontal distance away from the apex of this ramp. And our first challenge is going to be to find theta. Now, when I find theta, and I suggest that you do the same, we have from our little graph, we have some information that we can get on this right triangle. Now what I used, and I suggest you use, is get the largest side adjacent and the largest side opposite that you can possibly get. This graph has a readability of about a half a unit. So the larger the numbers you work with, the less that half a unit is going to affect you. So a small number, a half a unit, can be a large error. A larger number, that half a unit, is going to give you a much smaller error. So that's why I used this 5.5 side adjacent and side opposite, and I get kind of lucky. Those are some nice numbers, and on the problem that I'm working with, that will give me a theta of 45 degrees. And we're going to need that because we're going to have to do a force analysis of this mass sliding down the ramp. While we're at it here, we're going to do a little bit more trigonometry because one thing I need is this distance that I slide down the ramp. Okay, what I'm going to do now is I know I'm starting off at rest, and I'm going to slide down this ramp. Theta I've determined. So I need some acceleration because ultimately what I'm after right now is to get the velocity of this mass when it hits the end of the ramp. Okay, so let's go to a free body diagram of our mass. And the first thing, of course, we want to do is we want to break our weight vector up into parallel and perpendicular dimensions. First thing we can do then is that gives us what our force normal is going to be. And then from that force normal, I can then figure out what the force friction is going to be. Now I'm ready to go to Newton's law. The force normal and the perpendicular component of weight are going to cancel out. So I'm left over with two forces, the parallel component of weight and the friction equals mass times acceleration. And that's what I'm after. I'm after that acceleration. Now we go back to the kinematics of the problem. We've got this block initially at rest, the acceleration that we just figured out, and that's what I'm after, the velocity at the end of the ramp. So I use one of my kinematics equation. I'm starting at rest, the distance I know. So my unknown that I solve for is the velocity of the end of the ramp. We're getting a little closer, but we're not done yet. The next thing that this problem becomes is now a projectile motion problem. Now, something that we're not quite used to here is I start off my projectile motion with my initial velocity below the horizon. But I'm going to handle it the exact same way. I just need to be very careful about how I substitute into equation 4. Distance in the x is ultimately what we're after, but distance in the y in my kinematics equation number 4 is going to help me solve for time. Notice the distance in the y is negative, and very important, notice the initial velocity, y component, is also negative. All right, so I'm not using initial velocity, I'm not using that speed off the ramp, I'm using the y component of that velocity off the ramp. Now I've got a quadratic to solve here for time, and once I do that, now I've just got one last step to do. I am now taking the x component of the initial velocity off that ramp, multiply it by the time that I computed, and now I get the distance in the x, which is the horizontal distance from the end of the ramp that the object will land. And that completes the problem.